Hi, this is our video lecture for General Physics 2, and this lecture is for Wednesday, the 8th of April. I'm actually doing it on the 9th of April, but it is for the lecture that would have been held the 8th of April. So where we're leaving off, we're talking about electromagnetic fields, and one feature of electromagnetic fields is the use of eddy currents. Okay, and it turns out that um, as you're pulling something through a magnetic field, the downward flux of the loop on this side is decreasing, the downward flux on the loop on this side is increasing, okay, and then that will allow this to be pulled. However, if you've got a braking force, that will create what's called an eddy current here, and that eddy current will lead to a force in the opposite direction, okay? So as these are clamped down, then this will create a change in flux in the different loops, and these eddy currents will cause the whatever object is moving through these magnets to slow down. So this is how magnetic braking works when you have slow trains or transit system vehicles. They just use a series of magnets. Okay, in terms of induced fields, a changing magnetic field will induce an electric field and vice versa. Okay, so if I have a magnetic field, let's say if it's going through a solenoid or something like this, and the magnetic field is increasing, then that will induce a current in this loop without any type of battery source. Changing electric field will also induce a magnetic field. So if I have a region of increasing magnetic field, then that will create an electric field even if there isn't a wire for current to flow through. So when you have a conducting loop, your changing magnetic field will induce current. So if here the magnetic field is going into the page and it's increasing, then you would expect that the opposing magnetic field would come out of the page, and then that would lead to the right-hand rule, and that would say that the current would go counterclockwise. Now that current is induced by the fact that there's an electric field that's also moving counterclockwise that would be there even if you didn't have the current carrying loop. Okay, so the current just comes from the electric field that is associated with the magnetic field, even if you took the loop away, there would still be an electric field. Okay, so if you have a region of increasing magnetic field going into the page, the induced electric field is going to oppose that and then will turn counterclockwise. So if we've seen electric fields where we've created electric fields just by point charges or different types of charges, that's called a Coulomb electric field. But if an electric field is created by a magnetic field, then we call that a non-Coulomb electric field. Okay, so just by changing the magnetic field, then you get an electric field that is associated with it. So changing electric field creates an induced magnetic field. And these magnetic fields and electric fields can sustain themselves free from charges and currents. Okay, and these took on the form of electromagnetic waves. So magnetic waves look something like this, where you have in the y-axis, you have an electrical field, okay, an electrical wave. And in the z-axis, you have a magnetic field and a magnetic wave. And then the wavelength is the difference in the peaks, regardless of whether it's electric or magnetic field peaks. That's the wavelength. And the velocity is just the velocity of light. E and B are perpendicular to each other, so the electric field is perpendicular to the magnetic field. E and B are in phase. And so the crests of the electric field and the magnetic field are also at the same time and at the same magnitude. So the zeros, the crests, and the troughs are all going to be at the same time between the electric waves and the magnetic waves. Okay, so your right-hand rule for electromagnetic waves then is that your pointer finger is the electric wave, your middle finger is the magnetic wave, and your thumb is a velocity of light that's a velocity of the energy wave that is emanating through space. Okay. So electromagnetic wave is a transverse wave. It has a perpendicular component to it. And electromagnetic waves can exist at any type of frequency. Okay, so you can have a very, very high frequency or a very, very low frequency. And all electromagnetic waves travel at the speed of light. Okay, and at any given point in the wave, the electric and magnetic field strengths may be related to c, the speed of light. So the electric field is equal to the magnetic field times c, the speed of light. So let's try an example. So remember, the electric field is your pointer, magnetic field is your middle finger, and the movement of the wave is your thumb. So if we take the electric field with our pointer and we point that to the right, and the magnetic field is our middle finger, so you kind of have to sort of turn your wrist around so your wrist is facing up. Magnetic field is facing up, then our thumb is the direction that the wave is moving, and that means that the wave is moving with our right hand along with our thumb, and it's going into the plane of the paper. So A is the right answer. Okay. The intensity of an electromagnetic wave is measured in watts per meter squared, and that's the power of the wave that impinges on a surface area A. Okay, so the intensity is just the power divided the area by the area in which the power is dispersed. Okay, we can also take that a little bit further. So our intensity of our wave is equal to our power divided by area. That is equal to 1/2 times the speed of light times the emissivity constant times the electric wave squared. And if we recognize that this is just equal to C times B, okay, then this becomes 1/2 C times B naught squared divided by mu sub 0, which is our permittivity constant. Okay, so that the intensity then relates to the electric field and the magnetic field. Okay, so let's say we have a microwave oven, and the microwave oven has an intensity of 5 kilowatts per meter squared. And the magnetic waves are 2.4 gigahertz. And we want to know the strength of the electric field and the strength of the magnetic field. So we know that intensity is just power over area. Okay, that's given already. And we can relate this to our electric field by the speed of light times the emissivity constant times the square of our electric field. So we can back calculate what electric field would be equal to if we have intensity. Okay, so I'll switch over to the document camera really quick. I can do that. There's my hand. Okay, so let's get the document camera out. So intensity, let me get this lined up a little bit better. The camera's kind of at an angle. There we go. Okay. Intensity is equal to 1/2 have to go back and cheat, so I'm going to look at this really quick. C times emissivity times our electric field squared. Okay, so I just solve for electric field. So E naught is equal to the square root of 2I divided by C E naught, our emissivity constant. Okay, so I have then 2 times, go back to our example problem, 5,000 watts per meter squared. Okay, back to the document camera, divided by the speed of light, 3.0 times 10 to the 8th meters per second, times our emissivity constant, which is 8.85 times 10 to the negative 12. Gotta look at the units again. Coulomb squared per Newton meter. Check on this. Coulomb squared per Newton meter squared. All to the 1/2 power. Okay. So we get our calculator out. We can calculate that. So we take 2 times 5,000 divided by 3 divided by 10 to the 8th divided by 8.85 divided by 10 to the negative 12th. And then we take the square root of that. And that gives me a value of 1941. Okay. And our units are going to be a little odd here. We have to do some dimensional analysis. Okay. So our electric field is 1941 newtons per coulomb. Okay. Then we switch back to magnetic field. Okay. So a magnetic field, I is equal to 1/2 C times mu sub 0 times B naught. Okay, but we also know that E is equal to E naught equals C B naught. Okay, so E is equal to speed of light times B naught. Okay, so B naught is just equal to E naught divided by the speed of light. Okay, so I calculate that. And that gives me a magnetic field of 6.47 times 10 to the negative 6 Tesla. Okay, so that's our magnetic field. Okay, so let's go back to the next example. Okay, so we have a digital cell phone, and it has a total power of 0.6 watts. It emits at a frequency of 1.9 gigahertz, okay, which is something we don't need. And at a cell phone tower 2 kilometers away, we want to know what the intensity of the waves is. So we assume that the wave spreads out uniformly in all directions. Okay, so going to the doc cam, so we have a cell phone here, and it spreads out uniformly in this sphere of radius 2 kilometers. Okay, P is equal to 0.6 watts. R is equal to 2,000 meters. Okay, and so the surface area projected is actually the surface area of this sphere, and the surface area of the sphere is 4 pi r squared. Okay. Okay, so just to find intensity, that would just be power divided by area. So that's going to be 0.06 0.60 watts divided by 4 pi divided by our radius, which is 2,000 meters, quantity squared. And then that gives our intensity. So we have 0.6 watts divided by 4 divided by pi divided by 2,000 squared. And that gives me intensity of 1.19 times 10 to the negative, I'm going to cheat. That's 1, 2, 3, 4, 5, 6, 7, 8. 10 to the negative 8 watts per meter squared. Okay, so that's the answer there for the second example. Okay, so all I've done is I've taken my power, I've projected it over a certain cross-sectional area. Okay, now in terms of polarization, the electric field and the magnetic field are perpendicular to each other, and the electric field vectors and the electromagnetic waves lie in a plane that's perpendicular to the direction of propagation. So that plane for the electric field vectors is called the plane of polarization. Now, most natural sources of electromagnetic radiation are unpolarized because they're at many different angles. Okay, the resulting wave that you see that's not polarized is just the superposition of many, many polarized waves with electric fields in all possible directions. So you see the resultant of many, many different waves that are all polarized, but they're all coming in different directions, so they look like they're diffuse. So, but if we use a polarization filter, a polarizing filter, we can create polarized light, and we can see the electric wave in only one plane. Okay, so the plane of polarization here is the y plane, or the y-x plane. Okay, speed of light is moving in the x direction. The electric field is moving vertical if the wave is moving towards you. The electric field here means that the wave is moving away from you. And then you can have polarization, which is 30 degrees from vertical. Okay, so when you have a polarizer, you have a polarizing axis, and that will allow only certain wavelengths or certain angles of light to come through. And so that will polarize the light so you only have an electric field in one direction. So the transmitted light is the power intensity of the transmitted light is equal to the power transmittivity of the incident light divided by or multiplied by cosine theta squared. Okay, so if you have a polarizer, and your polarizing filter has a intensity of 2 watts per meter squared, then how should the second polarizing filter be arranged to decrease to intensity of 1 watt per meter squared? Okay, so we can determine what cosine theta is. So we go back to our previous equation. The transmitted light is equal to the incident light times cosine theta squared. I'll get a fresh page here. Okay, so if the transmitted light is 1 watt per meter squared, and the incident light is 2 watts per meter squared, then we plug that in. Okay, or cosine theta squared equals 1/2. We take the square root of both sides. Okay, so cosine theta equals 1 over square root of 2. So cosine theta, is equal to 0.707. Okay. And so if I take arc cosine, then that means theta equals 45 degrees. So the angle at which I would have to polarize the light is 40 degrees from the incident angle, and then that would cut out half the light. Okay, now all of this comprises what's called the electromagnetic spectrum. And you probably have had classes before where they've talked about electromagnetic spectra before, and you can see that as the energy goes up, then you get greater intensity of light, and the wavelength gets smaller and smaller. What we see as visible light is right here in this very small band. And then as the wavelength gets larger and larger and larger, then, go backwards, the intensity of the light, photon energy then becomes less and less and less. So the light waves are carrying less energy. The more that you get to larger wavelengths, the more the light behaves like a wave. The more you get to smaller wavelengths, the light behaves more like a particle. Okay, so there's two different models. There's a wave model of electromagnetic radiation, and there's also the photon model of electromagnetic waves. And you can see that if we use a camera called the CCD camera, and we look at a photo at different levels of light, you can see that the picture, as we increase the light intensity, looks more like a continuous just field. You can see it's a phase, but it becomes more pixelated and looks more like particles the more that we decrease the light intensity. Okay, so these are particles that are arriving at the camera or the detector, and as we decrease the light, then it looks much more particulate. Okay. Um, the energy of a photon, okay, this is just an individual packet of light, is equal to Planck's constant times the frequency. And Planck's constant is 6.63 times 10 to the negative 34th joules seconds. So if we multiply that by frequency, which is in inverse seconds, then that will give us the energy in joules. Okay, so in the photon model, all electromagnetic waves consist of discrete massless units called photons. Photons travel at the speed of light in a vacuum. Each photon has the energy of h, which is Planck's constant, times f, the frequency. And if we superimpose a large number of photons, then it will have a characteristic of a continuous wave. So let's say we have a gamma ray and it has a frequency of 2.4 times 10 to the 20th hertz. Okay, so that's pretty high frequency. So we just, to get the individual energy, so we just take Planck's constant, which is 6.63 times 10 to the negative 34th joules seconds. What's our frequency again? 2.4 times 10 to the 20th hertz. All right, hertz is reciprocal seconds. And that means that the energy of an individual photon in this case is 1.5 times 10 to the negative 13th joules. Okay, not much, but that's a pretty energetic photon. Okay, and then let's say we look at a typical cell phone. And it emits radiation at a wavelength or at a frequency of 1.9 gigahertz. We want to know what the wavelength and the energy is for an individual photon. And so if a phone emits 0.6 watts, how many photons are emitted each second? Okay, so let's tackle this problem. So we know that the frequency is 1.9 times 10 to the 9th hertz. Okay. Our power is 0.60 watts. Okay. Planck's constant is 6.63 times 10 to the negative 34th joules seconds. Okay, and the speed of light, c, is 3.0 times 10 to the 8th meters per second. Okay, so we switch over to our document camera. Got all the constants written out here for this new problem. Okay. So we know that the speed of light is equal to the wavelength times the frequency. So we just take the wavelength is equal to speed of light divided by the frequency. So here we have 3.0 times 10 to the 8th meters per second divided by 1.9 times 10 to the 9th hertz, which is reciprocal seconds. And that gives us a wavelength of 0.158 meters. Okay. Now, if we want to know the energy of the photon, that's just equal to our frequency times Planck's constant. Okay, so that would be 6.63 times 10 to the negative 34th joule seconds. Joule second, not joule per seconds. Times 1.9 times 10 to the 9th hertz, which is reciprocal seconds. Whoops, I did that wrong. 6.63 times 34, 10 to the, okay, there we go, times 1.9 times 10 to the 9th. Oh, I did that wrong. Okay, try again, Brian. 6.63 times 10 to the negative 34th, okay, times 1.9 times 10 to the 9th. Okay, so that would gives me 1.26 times 10 to the negative 24th joules. Okay, so that means that the energy of a photon is 1.26 times 10 to the negative 24th joules. If my total energy is 0.60 watts, which is 0.60 joules per second, then the number of photons is equal to 0.60 joules per second divided by the energy of a photon, 1.26 times 10 to the negative 24th joules, and that will give me the number of photons per second. So we go ahead and calculate that. Try again. I am striking out today. So that gives me 4.76 times 10 to the 25th photons per second. Okay, so that's how many photons then would have to be generated in order to provide that type of energy. So that's how many photons are being emitted in energy terms out of your cell phone. Okay, so we'll go back to the PowerPoint presentation. Done both of our examples. So radio waves have very long wavelengths, but very low photon energies. And these are best described using Maxwell's theory, which is more the wave theory of light. At the other end, we have X-rays and gamma waves. They have very short wavelengths and very high photon energies. And these are described more as photons in the particle theory of light. And radio waves and microwaves are produced generally by the motion of charged particles on the antenna. So when you have a positive charge on top and a negative charge on the bottom, that creates an electric field. And then the polarity really changes, negative charge on top and a positive charge on the bottom, and that changes polarity. So the electric field goes up and down as the charge polarity on the antenna changes. Okay, and you get an electric field that goes up and down depending on whether this is negatively or positively charged on the antenna, and then the magnetic field goes in and out of the page. At higher frequencies of light, infrared, visible light, and ultraviolet, the antennas are individual atoms, so you see atomic radiation at that point. Okay. And nearly all the atomic radiation that we see in our environment, this is infrared light, is thermal radiation due to atoms moving around. Okay, and we see light in this particular range here. And so when you see thermal radiation at a temperature of maybe 3,500 degrees Kelvin, then the peak temperature or the peak wavelength is outside of the visible range. But as it gets hotter, then you see it orange. And then as it gets hotter and hotter and hotter, then it will appear to be yellow, green, blue, and even then white light. Okay. So the peak is related to the temperature by a constant 2.9 times 10 to the 6 nanometers Kelvin divided by your temperature in Kelvin. Okay. Some animals can see thermal radiation, so they can see warm-blooded animals. Here's a snake, and the snake's eyes can see thermal radiation, so it highlights the mouth. And then in terms of X-rays and gamma rays, these are high energy photons emitted by electrons. And if the source of the photon is nuclear, then it's called a gamma ray. X-rays and gamma rays are ionizing radiation. Each photon has enough energy to ionize atoms. So it can create ions from atoms, and this will generate cellular damage in humans. Okay. X-rays and gamma rays are very penetrating. Some of them can penetrate directly through concrete blocks. Okay. And I think this is an example problem that I had before. This is a coil within a coil. This is from a different chapter. I'm going to go ahead and skip this example for this particular chapter. This was something that I was using as a review for an exam. So what we'll do next is on Monday, when your homework is due, then we will review, you'll have a review session, which I'll do on YouTube for your exam on Wednesday. On Wednesday, your exam will be posted online. You will have the entire day to finish it, and it will consist of 5 or 6 problems from chapters 22, 23, and 24. Also, on Monday, I will give you your homework assignment for chapter 25, and that will be due at the final exam. Okay, no, I'm sorry, that'll be due Friday. We'll make that due on Friday. So, okay, and that's it for this chapter. Okay, this is for Wednesday, and Friday is a holiday, so have a good weekend.